So today I'm pleased to introduce today's session, Vector Database for Enhanced Classification, and our guest speaker, Alessandro Saccoia. He will talk about vector databases for enhanced classification and how they use Milvus for handling large-scale document collections. Alessandro is a data-driven marketing and AI solution expert. He has extensive experience in international companies like Nielsen Media and Vodafone. He's also leading data science and product team focused on applying machine learning to business challenges. He's also teaching AI and data-driven marketing at the IULM University in Milan. Welcome, Alessandro. The stage is yours now.
Thank you, Stephen. Yeah, thanks for the introduction. That was perfect. And sorry, everyone, for my throaty voice, but I just got sick today, so I'm getting sick right in this moment. Okay, let's get to the presentation. One sec. Sorry. Sorry, 1 second. Chrome tab. There we go.
You can go. We see.
Thank you. Okay. Well, about me, I just got introduced. Thank you, Stephen. And so just about my current focus, we've been like starting a startup in the last year that focuses on enhancing policy understanding and driving informed decision making in the public sector. So we have an attorney that works with us, and he's super expert about everything that is about public policy and lawmaking. So these are our current focus, but we're actually creating products and algorithms that can be used in a more generic way. In particular, we all focus, and our background is in knowledge solutions. So we have out at the moment a few products. One is Policy Manager that is aggregating news according to topic and policy areas, and that is why we need classification. Stream Scope, that is a real-time broadcast analysis tool that can be used to extract knowledge in real time from, for example, parliamentary sessions, or like recently for commissioner designate from the EU Commission. And we focus on policy and lawmaking. So our founding team, as I said, includes an attorney and a couple of people that are very expert in quantitative analysis. Because of this, we try to create AI agents that can give our clients and customers an advantage in understanding what is going on in their sector. So I give you a few examples of what we do because I want you to understand why we needed a very fine way of classifying documents. In this case, this product that is live is used to transcribe, diarize, and classify live streams and classify them according to EU policy areas that are given. They are quite a lot, and they can overlap somehow. So our clients, we wanted to give our clients a system that does not hallucinate and that can have like a very laser-like way of classification. Maybe at the end of the webinar, I will also show you this interface live. Another thing we do is like classic reg style projects, but so why are we talking about Milvus? Because in all our products we use Milvus. Also, when there is a reg involved, so considering that we are striving for grounding, so giving trustworthy responses, multimodality. So of course we ingest documents of all kinds, and explainability. So for example, in this UI, you see that we actually in our reg style solutions, we are showcasing those steps in the chain of thought fashion. So we actually want to always give our user the cognition of what kind of data the AI agents have used to formulate their final answer that is here. And because of that, of course, we can handle text, PDFs, videos, as you just see, and audio files as well. All of these for managing the knowledge, we use Django because it's a very robust system. It's made in Python, and we are all we all have a Python background. And we use a parallel Milvus database. So we have hooks that whenever a new document is added to our Django backend, it's also added in our Milvus backend, because we want to use Milvus for its search capabilities, as a vector database, and we use while we use Django for keeping all the relational database. So all the products that we are doing have this common characteristic of having a backend with Django that is somehow parallelized in Milvus. And in fact, this is something that at the beginning, when we were starting out, I was trying to understand if it was already made. It was not, but to us, using the Django primary key as Milvus primary key became really natural, and the two systems work really well. Actually, we just created one wrapper class, and then everything is basically working seamlessly and transparently. Other technologies we use are Guardrails AI, Milvus, Neo4j, because we use quite a lot of knowledge graphs, and also MediaWiki, because we love MediaWiki. I'm a Wikimedia member, and so we think that somehow it's a good way to use it in a semantic way. Okay, let's get to the main point. So we have a technical challenge in everything that you've seen. We need to evolve from basic classification, keyword-based, for example, to semantic understanding in domains that are very jargon-heavy, jargon-rich. They are also evolving, and they're really deep and vertical. If you think about policy, each month there are new words that can be associated in a classification, and also if you think about it in a vector space, if you take, for example, generic or general embedding models, the vector space of two fields of a policy area, two fields of policy areas are very close in vector space. And also, we have quite a lot of policy areas. So if you consider, I will show you in one of the next slides, that there are 32 official policy areas in the European legislative system. You can see that we cannot rely on any zero shot, for example, classification. So we had to engineer a better solution. So there are some good things about traditional document classification that we have inherited. Just to give like a historical background, remember before neural classification, there was pre-processing, vectorization, bagel words, TF-IDF, that is the sparse kind of search. Named entity recognition, so you go, you check out which are the corporate names, which are the toponyms or names, etc. And some manual feature engineering. And on these features, normally it has always been built some kind of classifier that can be support vector machines, random forests, or other kind of classifiers. Jumping to the last few years, Of course, not taking a look at all the LSTM, for example, based ways of classifying documents, we can see a few approaches. So if I have an unknown document and I have a corpus that is made of, let's say, 32 categories, what are my choices to classify this unknown document into one category, the most important one, or multiple categories if there is an overlap, but also with a distance score from these categories. So one option is to use embedding-based classification. So converting the text to vectors using pre-trained models, calculating the category centroids for the training corpus, and then each new document see to which of these centroids is closer. But this means to use a generic pre-trained embedding model from OpenAI or open source embeddings, for example, also BERT-based. And we experimentally found out, so I also want to give a warning, everything we've done, it's really experimental, and actually it's something that gave us the best results for our domain. Maybe on other domains it will work better or worse. So in our case, this embedding-based classification didn't give us very good results. So we normally start with an input sentence, we check the embedding, we pass it through an embedding model, and then we see what is to which centroid is closest. The other way of the other approach to classification could be by fine-tuning transformers. So we give an input sentence to a encoder-only transformer like BERT, for example, and then we put on top a classification head. This is normally the hugging face style kind of classification. So whenever we ask the Hugging Face transformers library for a classification, it normally gives us a way to fine-tune just this classification head by putting normally a fully connected layer on top of BERT, and that is going to be fine-tuned just the classification head, or there is the possibility of fine-tuning the whole system down to BERT. But still, like, it requires extensive labeled data, and it's kind of a black box. I mean, I don't really know how BERT was trained, so probably it could. We didn't know what was in there. We go to the next possibility, and I don't like this one too much because it's zero and few shot classification by giving GPT or Claude or whatever a huge prompt and asking for a structured JSON out, giving the possibility, the possible classes as an enumeration or in the prompt, and then parsing this prompt. Like in this case, I give a long prompt telling to provide the answer with in JSON format, and then I give the input text. Why I don't like this? Because it's completely black box. There is the risk of bias, and in our case, we have 32 categories. So we tested it, and we found that actually, by splitting into a train test and a test set our initial corpus, the metrics, so the accuracy of the metrics was really bad, actually, the confusion metrics. So we went for a hybrid approach that actually uses Milvus. And we took, in a very experimental way, the best of the two worlds somehow. So from traditional methods, we used KeyBERT. I will show you in the next slide what KeyBERT is about. It's a very thin algorithms, but algorithm and it works really well. We took TF-IDF. In fact, we are talking about hybrid search, and we use KNN. that is a simple, interpretable classifier. And from the neural approaches, we took embeddings, BGM3, that is the embedding model we are talking about today, and we use a modern vector database, Milvus, for efficient hybrid search. So the pipeline from above, it takes a text. There is an initial language detection that we use to set the language of NLTK for stop word removal, but these are like very common pre-processing steps. We give the sentence to KeyBERT that extracts keywords. So KeyBERT is a special like algorithm that uses BERT to extract which are the most important keywords given a text. And we create a new transformed version of the input text, and we give that version to the sparse vector, and we give the original, well, without stop words, but we could also as well give it with the stop words. We give the original sentence to be transformed with the dense vector. So this approach somehow, well, first of all, it gave us the best results, and it's kind of a hybrid. I will show you now how we work with KeyBERT, but please take in consideration that somehow here we are creating a new sentence that is really likely to be well treated by the TF-IDF algorithm. So we're kind of cheating, let's say. So we are augmenting the sentence to exploit how TF-IDF works. That is, it works with the term frequency. So we are somehow artificially inflating the term frequencies of the keywords we care about. And in this way, when we ask, so when we will get to the KNN part, we got really good results because the sparse TF-IDF version of this algorithm works really well. And like as a spoiler, we are actually retrieving with the weight of 50% to dense vector that gives us the whole meaning of the sentence, of course, and 50% TF-IDF. That in this case we use because we are sure that in such a domain-specific jargon and language, we still want to use keywords, because keywords in politics, in lawmaking, the name of the committees, for example, those are really important names. We cannot just retrieve documents for classifying them just based on meaning. We still want to keep some meaning, but we want to, this is a way to highlighting the value of the specific keywords that belong to our domain. So what is KeyBERT? KeyBERT is a very straightforward technique of extracting keywords from a text, and it's actually it extracts the words that have the highest cosine distance in their single word embedding to the whole document embedding. That means that it extracts the words that are the most representative of the document they are within, and those are the keywords. So this is like very straightforward, as I said, and it can be downloaded. It works really well, and it always, from our experiment, it always gives a very high quality of keywords. So just to show you KeyBERT in action, so if this is part of the speech of the first system that I showed you, StreamScope, and this is a commissioner designate at the beginning of November. He was talking. So this commissioner designate is designate for climate. Of course, he was speaking about climate, and this is how, after treating it with BERT, this is the output of KeyBERT. So we have the most important keywords are climate proposal 2015, emission proposal, and this is, I mean, this, as you see, it works quite well to extract keywords. Just one warning, we fine-tuned the version of BERT to the legislative documents, because in any case, it's an unsupervised kind of training. So we had the legislative texts tagged by people at the European Commission, at the European Parliament, tagged very well also, because we did some, of course, some data visualization, and we saw that the clusters were like quite far away one from each other. And we did the fine-tuning of BERT for meshed language modeling. That is the kind of downstream task of training objective where words are removed from within the sentence, and that actually one of the two objectives BERT was trained for. So we really fine-tuned the core of BERT in this way, and since KeyBERT uses BERT, this gave us the possibility of using the new keywords that come up. So if we have recent documents, we know that KeyBERT will know those words, and if one word is really important, because BERT saw them in context, and so it gave it a good meaning for our objective. So we know that KeyBERT, if we do this fine-tuning, will be always updated and extract also very important keywords. So the result of KeyBERT is keywords plus the cosine distance from the whole document of each word. Okay, so let's arrive to how we did it, like how we put this in action. As I said, there are 32 categories in the EU, and so policy domains, and they are quite evolving. That is, every month there are new acronyms, new names that go in the that appear in the conversation. So we wanted to do a system that would like keep being updated. How did we train the system in an iterative way? So first of all, taking all the documents of the previous slide. So we have 32 topic areas, and we have quite a lot of documents that belong to each of the topic areas. We fine-tuned BERT for using them with KeyBERT on those documents that are official from the European Parliament. Then we do some pre-processing. For example, considering that some documents can have multiple tags, we just keep the ones that have a single tag, and so we skip some of them. And then through KeyBERT, we create a transformed document that by repeating the most important keywords found by KeyBERT. So, for example, the segment that I showed you before became, and this is has been cut, is truncated at the end, but it becomes something like this. So you can see that here we are somehow tricking the following TF-IDF system in giving more importance to keywords that we know that semantically have more importance. So basically we are using TF-IDF as a counter somehow, because we have already extracted quite a lot of meaning. But the cool thing is that through the Milvus hybrid search system, if we pass this kind of preprocessed document, we can use out-of-the-box Milvus as it comes. So we can use hybrid search with 50% weight on dense and 50% weight on sparse embeddings. And then we apply BGM3, and we insert the training documents in Milvus in a special training collection that we actually keep feeding. Every 15 days, we have a process that takes the last documents and iterates here, so that we know that this BERT that we're using eventually for transforming these documents will actually know the meaning of these new tokens. I mean, even if BERT uses word-piece tokenization, so acronyms are not a problem with BERT, we found out experimentally that it was important because those tokens that are surrounded as in normal embeddings that are surrounded by that context, actually by fine-tuning we give them the meaning that they deserve. And so in the process of keybert that I showed you before, they are kind of enhanced for the for the special TF-IDF treatment that we do later. This is for training system. So we end up with a training collection with all the documents with these two kind of, so a sparse vector with the transformed document, a dense vector with the original document. And then how do we classify an unknown document? So we do exactly as we did before. So we use keyword, our fine-tuned keyword, to get the best keywords out of that document. We apply BGM3 in the same way we showed before. So we have dense vector on the original one, sparse vector on the transformed document. We have a special API endpoint because we don't do this on a production server, of course. We have a GPU server with an embed endpoint that hosts this model. And then we retrieve the k closest documents using the vanilla, normal, like Milvus hybrid search. And since they are retrieved in order of distance, closed documents that have been found to be closer in both the dense word and in the sparse word are retrieved first with of course, and they must have more influence. And we do a sort of voting, such as the similarity score determines the voting power of each of the training documents, and each document is actually voting for its own category. So at the end, we have a sort of weighted KNN, you can call it. So we sum up the weighted votes for each category, and we choose the category with the highest total weight. And this is an example. So if we have k equals 5, and we find that these are the first 5 documents, and we have these kind of similarity, and they have, since it's, of course, they were labeled, we know that category A eventually wins with a weight of 269 versus category B with a weight of 165. And so this is the KNN part of this webinar. And these gave us very good results. I'll show you how did we benchmark it actually in the end. Another question could be why BGM3? Actually, the experimental results, and you can find this article on Medium. First of all, it's multi-language, and being multi-language is and while it is multi-language, it's really good at most languages. It's actually surpassing in mean reciprocal rank, that is this metric that shows how good a model is at retrieving the most relevant results. It surpasses most commercial embeddings. So OpenAI, for example, these are the two OpenAIs, and actually the mean of the accuracy in retrieving the correct documents in BGM3 is surpassing in all languages all the other options. This is why we use BGM3, and also because it was embedded in Milvus, and we built a lot of stuff on top of Milvus, so it was natural for us to use it. Last thing, how we benchmarked this? It's not exact science. I mean, this was made. I mean, we are coders. We don't do. We do the things that actually work well for us and for our specific domain. It worked really well. How we did it? So basically, we split our training data set into training and validation sets, and then we check the confusion metrics. And actually, this whole pipeline gave us a very, very good accuracy on all the 32 classes. Also, we have a human in the loop, because remember, we have our policy specialists, and actually they were really happy about the algorithm works. We do have next steps. I mean, this system was made quite fast, also to create an MVP. And of course, I think that some of this complexity could be avoided by fine-tuning our own version of BGE M3. And the other thing is that there is no out-of-domain detection. So if a text is talking about, I don't know, a recipe in cooking, we will still be classifying it as policy. But the good thing is that everything we try to classify is policy, so we are always somehow in domain. So this could be something nice to have for the future. I give you a small demo. This is the last thing for the broadcast system. I need to change window. There we go. So it's called the stream scope, and so. So this is the recording. It was made basically after 40 minutes from the end of this 3-hour long speech. We had, like, the whole pipeline had already created this classification. We do quite a lot of things, because we segment into parts. We understand whether it's a question and there is a follow-up answer. But regarding our webinar of today, we are actually tagging into policy areas. So if I select that when he's talking about enterprise, I get just the segments that talk about enterprise. Of course, we have also a full text search. We have summaries. We have the possible other topics that have been talked about during this segment. And last thing, of course, there must have been a chatbot somewhere. We can ask the person, for example, what are your priorities as a commissioner. And also here there is some Milvus, because the system will actually answer about give a good answer to this question. So based on the hearing transcript, Franz Timmermans' priorities are blah, blah, blah. But actually, as I said, we always want to ground our answers in something that is real. So we also give the actual quotes from the commissioner. So basically, I think that any stakeholder that is interested in knowing, considering that there were 80 hours of these videos, any stakeholder that is interested in knowing what one person had to say about a particular topic will just go here. Actually, we see it through the Google Analytics, that people use this part the most, because it can answer really well to all the precise questions. And this was it.
Cool. Thank you very much.
Thank you.
Thank you very much. Yes, we had one question in the chat, which is, so which LLM are you using here? Is it like Gemini 1.5, as you're saying it's multimodal?
Yeah, it is Gemini. Yes.
It's Gemini? Okay. Is it 1.5 then?
Yeah.
Okay.
Yeah.
Are you planning on moving to the 2.0 now that was released?
Yeah, I saw it
yesterday.
Yeah, I didn't have time today, but I saw incredible stuff. People talking to the UI. Wow.
Okay. And yeah, maybe I have one on my end. So like, Have you seen like a really big improvement with like hybrid search, for example, for you? Is it like a night and day improvement, for example, by using it?
Yeah, completely. Because, as I said, vector only search in this very deep, specific language, the points in the multidimensional
Mm-hmm.
space are too close. So vectors are like too similar, and you get somehow some random results. And at the same time, um, only sparse search was not the way to go. And this kind of hybrid search, we also did some uh, grid search on the parameter of how much weight to give
Mm-hmm.
to the two types, and we actually found out that 50-50 was the best.
Okay.
Just for as an information. Yeah.
Okay, interesting. Yeah, and I had a follow-up question, but I forgot. Ah, yeah, with Neo4j. So how's it like? Do you work directly with like GraphRag, for example, or you just with like different systems working
Sorry,
together?
can you
With Neo4j, you're using Neo4j, right? So is it like GraphRag based, or it's mostly like entity and then vector?
no, we do just entities. Actually, we're just starting using it now. We use
Okay.
Neo Extractor, that is an LLM that is specialized in open source, specialized in getting structured output, and it works
Mm-hmm.
quite well too. Because of course the problem is still text to graph. I mean,
Yeah.
I like to get graph to text, it's done, but the text to graph, I think that besides a lot of people talking about it, I still haven't seen like a general implementation, because of course it's like, I mean, it's really complicated to have a general
Yeah.
implementation of that. Yeah.
Okay, cool. Perfect. Thank you. I think that was it for my questions. I'm just gonna wait quickly to see if anyone else has a question. But otherwise, thank you. And for the people as well, and also the people that couldn't make it, like everything will be shared online. Everything will be shared on YouTube in a couple of days. We'll send it to our editors. So then it's also available there. But I think that's it, Alessandro.
That's
Thank you
all.
very much. Thank you for the presentation. And see you next time, everyone.
Yeah.
Bye.
Bye. Bye. Bye.